All right, let's look at another exam. Woohoo! Nice! Calc 3, of course, locally 2650, and a great exam. It's from fall 2024. And this was a semester when we started doing multiple choice. And so it'll be interesting to go through and look at those problems. Of course, we have our workout problems ahead. 10 problems in total. Lots of fun waiting for us. But before we do anything, we make sure we put our name on here because we want the credit. Yes. All right. Let's begin. Off to the races. So, starting with our multiple choice. First problem says find f sub xx for fxy equals log cosine 2x minus y. And so we say, okay, make sure we understand what's being asked. It says f sub xx. Now, this is a notation for taking the derivatives. We can't use the prime notation anymore because there's multiple variables. And so this says take the derivative with respect to x twice. And notice, yes, it is a function of two variables because there is this thing, this minus y. However, when we're thinking about it in relationship to x, when we take derivatives with respect to x, it will be a constant. And so actually, it's really a single variable calculus problem if you think about it. It just says take the derivative twice with respect to x. Like, all right, cool. So let's start. So we start by the first derivative, f sub x. Okay, so you have a log. If you have a log, write a fraction. The function inside the log, that goes downstairs. And now upstairs, take the derivative. Derivative of cosine minus sine. Leave the inside alone. And then keep working your way through. It's like onions. There are layers. And hopefully no tears involved with these layers. But okay, keep working the problem. Derivative of 2x minus y with respect to x. Remember, taking derivative with respect to x is 2. Now, before we take another derivative, you should always say, can I write this in a simpler way? More friendly. And yeah, sine over cosine, also known as tangent. So this is minus 2 tangent 2x minus y. So now we're ready. fxx says take the first derivative with respect to x and do the derivative again. You know, the idea is so nice, we'll do it twice. All right, well, negative 2 comes down for the right. Derivative of tangent, secant squared. And, all right, leave the inside alone. Times by the derivative of the inside. And the derivative of 2x minus y with respect to x is a 2. So minus 2 times 2 makes minus 4 secant squared 2x minus y. E. Minus 4 secant squared 2x minus y. Woohoo! Nice. All right. Progress. Oh, wow. Right out of the box. We're doing great. Number 2. Find partial w partial x if w is f of this and that, and partial f partial x of xy is this expression partial f partial y. Xy is 1 over x squared. Okay. All right. So what's being asked here? What are we being tested on? So let's think about what we have. We kind of have this sort of alphabet soup going on. We have x's and y's, and then we have s's and t's, and so we say, okay, this is, a collection of variable names. This is chain rule. So what's going on here is we say, well, f really depends on x and y. So this entry right here, this is our x entry, and this entry over here is our y entry. So we're like, oh, okay. So we have w, which is equal to f. That depends on x and y. And then x and y, well, they both depend on t and s. So now we say, well, what are we after? Well, we're after the following. We want to do partial w, partial s. And we say, all right, where does s show up? It shows up in these locations here. And so we say, all right, well, partial w, partial s is, if we do our rules, partial w, partial x, and this is f sub x, partial w, partial y, by the way, is f sub y. So that's partial f, partial x, times partial x, partial s. And then add, go the other chain, partial f, partial y, times partial y, partial s. Well, we're almost there. We say, all right, what is partial f, partial x? It's right there. Aha! Ah! Well, that's good. That'll make it easy for us to spot. So we have partial f, partial x is minus 2 times y minus 1 over x cubed. Do we know what partial x, partial s is? Well, come to x here. Take the derivative of x with respect to s. And if we think about this, this is really ts to the negative 1. So partial x, partial s, the minus ts to negative 2, or negative t over s squared. So times negative t over s squared. Okay, plus partial f, partial y, 1 over x squared, times partial y, partial s. Well, okay, now partial y, partial s, that's this piece. And what do we see? Well, that's pretty easy to take a derivative. We don't have to think too hard. Derivative with respect to s will be 2st squared. All right, now is this one of our options? No. Do we give up? No. Because wait, we say, hey, hold on a second. We know things. It's good to know things. And what do we know? Well, we know what x and y are. So we say, hey, wait a second. We can replace x by t over s. And we can replace y by s squared t squared plus 1. So if we do that carefully, we have minus 2, y minus 1 would become s squared t squared. Now x cubed would be t cubed over s cubed. But notice the x cubed is downstairs, so you flip it and you say, okay, so 1 over x is like s over t. So 1 over x cubed would be an s cubed over t cubed. All right. Okay. Yes? Yes, maybe. Yes. And then times, don't forget, that minus t over s squared. All right. Now, we can go to the next term. We actually have enough to answer the question now. I'll come back and say why we had enough. 1 over x squared. Okay, again, 1 over x is s over t. So this is s squared over t squared times 2st squared. Now, why could we actually have stopped? Notice they all have different powers of s. And so we just have to figure out what the power of s is. If we cancel our t squareds here, we see an s cubed. So we're looking for the s cubed. It's got to be the one with an s cubed. Or it could potentially be 0. Okay, all right, fine. We'll double check. Minus minus makes plus. Here, there's a t squared and a t upstairs and a t cubed downstairs. And then s squared and s squared cancel. And so we're left with a plus 2s cubed, another 2s cubed, which does indeed make 4s cubed. Whew. Oh, that is a lot of work for a multiple choice problem. Wow. But the ideas, not so bad. But it just, you have to go through it carefully. And kind of the hint that it's chain rule is you see how you have these expressions inside where you have the variables. Because if you think of chain rule, it's like, oh, f of g of x. Like that's our Calc 1 chain rule. So you said, oh, it's a function being plugged into the function. Well, that's what's happening here. It's functions of s and t being plugged in to the slots for x and y. Just have to work through it carefully and clean it up. All right. Well, we survived that one, right? We'll survive them all. We can do it. We can do it. No worries. No worries. I remember this one. I drew these pictures. Okay. Hopefully I can do it. All right. Given the function f of xy is x minus 1 quantity squared plus y minus 1, which of the following is a contour map, collection of level curves, for the surface given by z equals f of xy? So what we're seeing is we want to be like, there's a surface doing something, I don't know, but now we're going to slice, and we're taking different slices. And like a topographical map if you've ever gone on a hike. Now, how do we do it? Well, there's a couple ways to do it, but basically we say, what does a level curve look like? Because what do we see? We see parabolas going up, we see parabolas going down, we see circles. And so we just say, well, imagine we have a level curve. It looks like x minus 1 quantity squared plus y minus 1, in other words, the function, equal to some constant k. Well, we can solve for y. So we look and say, well, this is y equals minus x minus 1 squared plus k minus 1. Now, this k minus 1 doesn't really matter too much. It's really a shift. So we say, well, what does that look like? Well, x squared parabola minus parabola going down. Okay, so that's parabola going up, circle. So those are out. So it's one of D or E. Now we think about, well, what does the x minus 1 do? Does it shift it to the left, or does it shift it to the right? Well, because it's on the inside, that's going to be a shift. And you sort of think about what x would you have to make to get 0? Right? Which x, if you plugged it in, would be the equivalent of plugging in 0? Well, if you plugged in now x equals 1, that would act like your new 0. So 1 should be where 0 used to be. So normally we'd have it upside down at 0. We've shifted this direction. The answer is E. All right. Okay, good. Number 4. Use Taylor's formula to find the quadratic approximation of the function f of xy is 1 plus xy squared plus x squared y near the point 0, 2. All right. Now there's a couple of ways to do it. One way is we could do the whole problem, but it's multiple choice, right? And so let's take advantage of that. And we say, okay, how do we take advantage? Well, there's one not so bad way, is to say, well, let's say, what are we after? We're after the function at the point. Then we add the partial derivatives at the point times x minus 0, and the partial derivative of y at the point y minus 2. And then we go into the second derivative. So we have fxx times x minus 0 squared times a half. Don't forget that. That's an important thing. I can throw you off if you forget that. Plus fxy at 0, 2, x minus 0, y minus 2, plus 1 half fyy at 0, 2, y minus 2 quantity squared. All right, so there's a lot that we could have to go through and check, but we only have to know enough to distinguish. So looking at this, we say, well, they all have the same 1. Okay, so that's not going to be helpful. So we're not even going to check what f of 0, 2 is. It is 1, but whatever. They do not all have the same x coefficient, right? Here I see a plus 4, a plus 4. These are minus 4s, and here I see zeros. So let's focus now on this part. And let's see what we can get. Okay, so, well, let's take our f sub x. What is f sub x? And we have space up here. It is 0, y squared, and 2xy. Now, plug in 0, 2, f sub x at 0, 2 is 4 plus 0. Okay, so we want the coefficient for x should be 4. Okay, that rolls out B, C, and E. So we're down to A or D. Okay, good. Now, looking at A and D, we say, hey, this part agrees. This part agrees. Now, that tells us if we want to distinguish and say which one is right, I need to distinguish between those two, which means we need to go here. All right, so now, that's right. We're going there. So that's our fxx. So fxx, take the derivative with respect to x twice. All right, y squared is just going to go away. There's no x. And this will be 2y. So fxx at 0, 2 is 2 times y is 4. So now you might say, aha, it's the 4. Don't forget the half. It's a half times 4 times x squared, which means the 2x squared is the right answer. All right, and there you go. Now we could have computed fxy, we could have computed fyy, we could have computed f sub y, but we didn't need to, because we actually don't need to do the whole problem. We just need to do enough to rule out possibilities. And in that case, we were able to do it by looking at just 2 of the partial derivatives. All right, you know, it's one of those things. One of the advantages of multiple choice is you don't have to do the whole problem. One of the disadvantages is one small mistake. Oh, I forgot the half. Ah, they anticipated my mistake. So it's one of those things where it's like, do enough to make sure you got it, but don't overdo it. Use your time wisely. Okay, on to our next problem. Number 5. Which of the following is a critical point of f of xy is x cubed plus 3xy minus 6y plus 12? All right, so we have a beautiful function, polynomial. Mwah! We love polynomial functions. And so we say to ourselves, okay, what does it mean to be a critical point? And, okay, no boundary, no places where derivative would have issues. So that means we're after where the derivative, or in our case, the gradient, which is our basic stand-in for derivative, is 0. Well, that really says, look at where the derivatives are 0. F sub x equals 0. F sub y equals 0. That'll lead us to 2 equations, 2 unknowns. Solve for x and y. Life will be good. So we start by taking our derivatives. So we say, okay, f sub x. Take the derivative with respect to x. Treat your y's like constants. Derivative of x cubed, 3x squared. All right. Derivative of 3xy, 3y, right? Because remember, we're taking derivative with respect to x. Y is a constant. Derivative of 6y, 0. Derivative of 12, 0. All right. Set that equal to 0. And fy. Okay. Well, now we take derivative with respect to y. X is our constants. Derivative of x cubed, 0. Derivative of 3xy, 3x. Derivative of minus 6y, minus 6. Derivative of 12, 0. Set that equal to 0. Now we have 2 equations, 2 unknowns. But the second equation, I think we can solve that one. 3x minus 6 equals 0 tells us x equals 2. And we say, all right, which one of these has x equals 2? Well, not this one, not this one, not D, not E. So by process of elimination, we know the answer is C. For sanity check, it maybe isn't the worst thing to check. Hey, does that click with what we have here? Well, suppose x equals 2. If we come into this equation, we say the 3's go away, and y should be negative x squared. Well, negative 2 squared is negative 4. Whew! We did it. We did it. All right, that one wasn't so bad. I got to tell you, these multiple choice, kind of like a roller coaster. Some of them pretty straightforward, and some of them are like, ah! Well, it's an adventure. Enjoy the ride. Enjoy the ride. All right, that brings us to our last multiple choice problem. Okay, let's, fingers crossed, let's hope we enjoy this one as well. Let y be a function of x and z, defined implicitly by the equation 2x cubed y plus 3x z to the fourth is y to the fourth plus 4z. Find partial y, partial z. So let's be really careful here. Y is a function of x and z. So we say, y depends on x and z. And what are we after? We're after partial y, partial z. Okay, so we're taking the derivative of y with respect to z, not the derivative of z with respect to y. That's something different. So you want to make sure you're taking the right kind of derivative. Now, it turns out if you take partial z, partial y, you just flip the answer and you're done. But I suspect they may have anticipated that. So let's be careful here. Let's be the right amount of careful. So how do we go about this problem? Well, the key is make sure you understand what's downstairs. And we say, well, it's a partial z. So the moral is we're taking the derivative with respect to z. Y depends on z. What happens with x's? Treat x like constants. All right, so that's one of our thoughts we have in the back of our head. You know, x is like a constant. All right, it's a very small thought, but that says x a constant. And it does. Okay, so here we go. So we have the two sides, and I'm going to write them again. 2x cubed y plus 3x z to the fourth equals y to the fourth plus 4z. Okay, so taking the derivative with respect to z, step by step, very carefully. The 2x cubed is a constant, so this will come down as 2x cubed. The derivative of y with respect to z is the derivative of y with respect to z. The 3x is a constant, okay? Constants just come down. Derivative of z to the fourth with respect to z will be 4z cubed. Okay, so that's z to the fourth. Derivative of that is 4z cubed. Constant derivative. Equals y to the fourth. Now, here we say what? Y is a function of z, so we have to do chain rule. So we say, okay, bring the 4 down. Then it's going to be y cubed times the derivative of y, which is partial y, partial z. Okay, so this is our chain rule. Getting all of that, plus 4, take the derivative of z with respect to z, and you're going to get 4, right? 4z, derivative of z is 1. All right, so there we go. Now we switch into sort of more of our hunter-gatherer type mode. We say, hey, things with a partial y, partial z, they're going to go together, and then things without a partial y, partial z, those are going to go together. So we say, okay, cool. And so let's move things around. And we can move, say, if we move this across and factor out, we get 2x cubed minus 4y cubed times partial y, partial z is equal to, and then here we're going to move this across, and that's going to be 4 subtract, and well, we have 3 times 4 is 12, and 12x z cubed. All right, well, okay, so now divide. Partial y, partial z is 4 minus 12x z cubed over 2x cubed minus 4y cubed. Okay, now, does that look like any of our options? And remember, they may have done some simplifying. So let's see, does it kind of look like 2 minus 6x z cubed over x cubed minus 2y cubed? Well, yeah, notice how all of these are evens. So suppose we pull out a factor of 2 and cancel. So then, because it has like the right field, right? xz cubed, x cubed, y cubed. So this will become 2 minus 6xz cubed divided by x cubed minus 2y cubed, right? Because I just divide every term by a 2, which means our answer was A. Whew! Good. Now you'll notice there's a lot of tempting answers here. A lot of tempting answers. And what do I mean by that? Well, if we go further down the list, we say, well, we could do things such as flip things upside down, change the signs. And so, for example, here we just flip things upside down. And here we're like flipping, but changing the signs. So it's like, small details. Got to match in every single aspect. And so take your time. Make sure it exactly matches. Because if not, well, it's probably something else. All right. Well, that's number 6. And all right, I'm going to make a confession. I wrote this one. And so any apologies if you find it, Steve, but it's a good test to be like, are you paying attention? And make sure everything gets there. Because there's small mistakes, and this is capturing some of those small mistakes that you might make. All right. But now into the workout part. That's right. We're going to work it out. And the good news is now small mistakes don't kill us. All right, multiple choice, it's all or nothing. But here, it's like, okay, we've got a real chance, a real shot. So let's go for it. All right, number 7. And there's a lot of parts here. So let's see. Part A. We have this function f of xyz equals e to the xy plus yz. And we're asked, find the gradient of the function at the point 0, 2, 1. Okay, so first off, what is the gradient? Well, the gradient of the function is the collection, it's a vector of partial derivatives f sub x, f sub y, f sub z. So let's just take the derivatives in the order here, x, y, z. And so we say, okay, coming along, take the derivative with respect to x. Well, there's only one x. That's y and z are constants. So it's e to the x times a constant. So chain rule, constant comes down. Y e to the xy. The derivative of y times z goes away. It's a constant when taking the derivative with respect to x. F sub y, well, we have e to a constant y. So chain rule, constant comes down. So x e to the xy. And then the derivative of y times z will be z. Again, z is a constant at this stage. Z, f sub z, e to the xy, goes away. There's no z. Derivative of y times z, y. Oh, wait, yeah, y. It's not a question. It's a statement. Y. It's the variable y. Now, that's the gradient generically. We want the gradient particularly. It tells us to do it at a special point. Well, maybe it's special, I don't know. But at the point 0, 2, 1. So let's plug that in. Gradient f at 0, 2, 1. Everywhere where we see an x, we put a 0. Everywhere where we see a y, we put a 2. Everywhere we see a z, we put a 1. So this becomes 2 times e to the 0. E to the 0 is 1. All right, comma. 0 times something plus 1. So 2 comma 1, comma. And y is a 2. So 2, 1, 2. So there we go. That is the gradient at the point 0, 2, 1. All right, good. Progress. Now, find the directional derivative of f at p in the direction 3, 4, 0. Okay, so directional derivative, and that has several aspects. So how do we find a directional derivative at a point P? Well, the formula says you take the gradient of the function at your point dot the direction. And u here, remember, needs to be a unit vector. Now the good news is we did some work in part A. So we say, hey, I know what the gradient is. So we say this is 2, 1, 2, dot. We have our direction vector, 3, 4, 0. But wait, that's not the right direction vector. Because what is the magnitude of 3, 4, 0? Well, let's do a little bit of work on the side here. The magnitude of 3, 4, 0, well, that would be the square root of 3 squared plus 4 squared plus 0 squared. Square root of 25 is 5. So it's not a unit vector, it's a vector of length 5. Okay, that's all right. We can fix that. We have the technology. Divide by 5. Now it's a unit vector. Let's see, that wasn't so bad. All right, so we start doing our multiplication. We have 2 times 3, which is 6, plus 1 times 4, which is 4, plus 2 times 0, all over 5. 6 plus 4 is 10. Divide by 5 makes 2. So the answer is 2. That's the directional derivative in the direction 3, 4. All right. C. Find a unit vector u such that the directional derivative is maximum. Now here, you might say, well, how do we do that? This comes back to saying, do you understand what the gradient is? Now we're using the gradient up here. We said the directional derivative is the gradient dot u. So we say, well, how do you make the directional derivative maximum? Well, you just want to say, I want to make sure I'm pointing in the right direction. And so this here is properties of the gradient, and the max occurs in the same direction of the gradient. And so we say, well, that's very convenient. In fact, if it just said find a vector that points in the direction of the maximum, we could just write down the answer to A. But we have to make it a unit vector. So we say, all right, well, let's find that length of 2, 1, 2. And we say, well, that's the square root of 2 squared, which is 4. 1 squared is 1, and 2 squared is 4. Square root of 9 makes 3. So take your gradient, divide by 3, and we're done. All right. Okay, cool. And now it says find DUFP. Now, this is not the most clearly worded problem, but you might say, wait, what? What's the right U? But you'll notice here they were very careful not to use U in this. So you say, they must mean from up here. So it's using the U from C. So this is a continuation that says, all right, what is the maximum rate of change? Okay, so that's what that's referring to. That could have been a little bit clearer. I grant you that. But all right, so what do we have? Well, again, that comes back to say, do you understand what the gradient is? And we say, so this is the max rate, which is the magnitude of the gradient. But wait a second, we already found the magnitude of the gradient up here. So that means that the answer is 3. And notice it's only worth 1 point. So usually when something is worth 1 point or 2 points, it means that the answer is right there. It's just a matter of saying, grab it. Or it's like, put these two things together. And sometimes these point values are somewhat useful to help you figure out, wait, am I trying to overthink it? Or is there maybe something subtle going on? Things worth 1 or 2 points? Okay, it should be pretty simple, should be pretty quick. Things worth 5 or 6, there's probably subtlety. Make sure you haven't overlooked something. All right, well, there we go. Let's keep moving. Moving right along to number 8. Yeah. So we have the following. A level surface is given by the equation. F of x, y, z is x plus 2x cosine z plus 2y sine z plus y equals 5. Find the gradient of f at the point 2, minus 1, 0. All right, well, okay. So the gradient of f says, don't worry about this equals 5. Just this left-hand side, or I guess this middle side, if you will. And so we say, okay, well, gradient of f is f sub x, f sub y, f sub z, the collection of the partial derivatives. So we go through, take the derivative with respect to x. Anything with y or z is constant. Right? Be careful. We treat y and z like constants. Okay, so here, derivative is 1. Here, 2 cosine z. Those are constants. X is your variable. No x, no x. Comma. F sub y. No y. No y. 2 sine of z. And it's like 2 sine z is a constant times y. And then plus 1. F sub z. No x. Okay, derivative of cosine of z would be negative sine z. So that would give us minus 2x sine of z. Derivative of sine of z is cosine of z. So plus 2y cosine of z. And there's no z. Okay, so there we go. There's our gradient generically. Now we're going to take that and we're going to plug in our point 2 minus 1, 0. So we say, okay, gradient of f at 2, negative 1, 0 is, well, we're going to get 1 plus 2 times cosine of 0. Cosine of 0 is 1, comma. 2 times sine of 0, which is 2 times 0 plus 1, comma. Minus 2x, so that's going to be minus 4 times sine of 0, which is 0, plus 2y, so 2y times cosine of 0, which is 1. Okay, so that's 1 plus 2. That makes 3. And 0 plus 1 is 1. And 0 minus 2 is negative 2. So 3, 1, minus 2. Okay, so that's our gradient at the point 2, comma, minus 1, comma, 0. All right, now, part B. Find an equation for the tangent plane for the surface in A at the point 2, minus 1, 0. Now, usually problems build. So we say, okay, what did we find in part A? We found the gradient. But it's a gradient to a level surface. Now, what's true about gradients and level surfaces? They're perpendicular. Ah, ha, ha, ha. Okay, so this will be perpendicular to our surface. So this 3, 1, minus 2, excuse me, my voice is, I have to stop being so excited. This 3, 1, minus 2 is perpendicular to our surface. So it's perpendicular to our plane. That's tangent at that point. So sort of the great aha is that most of the work for part B was done in part A. So we have our normal vector, 3, 1, negative 2. And now these become our coefficients. In particular, we get 3x plus y minus 2z equals something. Now, how do we find the something? Well, now we use the fact we have to be at 2, negative 1, 0. So 3 times 2 plus negative 1 minus 2 times 0, well, that's 6 minus 1 minus 0, which is 5. So that's what goes into the box, which leads us to our answer of, and change colors here, 3x plus y minus 2z equals 5. All right, that's part B. And in essence, again, this is getting back, do you understand how to use gradient? Powerful tool, very useful tool, and in particular, it's used in helping us find tangent planes to level surfaces. It's excellent, beautiful. Okay, now, last part. Find a linear approximation to the function z equals g of xy implicitly defined by the equations in A around the point 2, minus 1, 0 in an explicit form z equals L of xy. Okay, now, it's like, what? Let's unpack this because, again, notice we didn't do a lot of work in part B. We probably shouldn't expect to do a lot of work in part C. It's a question of, do we understand what's being asked? That's a lot to do sometimes. So let's start with linear approximation. What does that mean? It means flat thing. What's our flat thing? Our flat thing is a tangent plane. Say, okay, great. So when it says find a linear approximation, it says, hey, you're trying to find that tangent plane. And we say, well, wait a second. We found our tangent plane. It's right there. And then we say, so wait, how are we not done? Well, it says have to do it in the form z is some function of x and y. So we're going to say, oh, solve for z. And that's a plane. So we say, okay, you just want us to take our tangent plane and solve for z. So let's do that. We'll swap the 2z and the 5, and we get that 2z is equal to 3x plus y minus 5. And now, if we divide both sides by 2, we get z is equal to 3x plus y minus 5 divided by 2. And we're done. That is our linear approximation, our tangent plane. And this, in some sense, this problem is sort of building up to say, well, how do you find nice linear approximations to implicit surfaces? And, of course, one way you can do it is run through implicit differentiation, do all that work. Well, this says, hey, you can find your normals pretty quickly. That means you can find your tangent planes pretty quickly. And now you just rearrange, and life is good. So there's our linear approximation in the form z is a function of x and y. Whew, okay, good. Well, let's keep moving. We want to make sure we leave ourselves plenty of time at the end to go back and admire our work. So, number 9, find all. Okay, got to find them all. Well, who knows? Maybe there's 1 or maybe there's 10. All the critical points of f and use the second derivative test to classify. Ah, cool. I always like these types of problems. And the different types of classifications, local min, local max, or saddle. So this is always going to be functions of two variables, f, x, y. And when you have a find and classify like this, we always go through 2 stages. So let's talk about stage 1. So stage 1 is the find. So, all right, so we're in the find mode. And so this says, set your gradient equal to 0. Well, again, that really means take the partial derivatives and set them equal to 0. So for us, we say, well, let's take the derivative with respect to x. We're going to get 6x minus 6x squared minus 0, because we're taking it with respect to x, plus 6y, and then we're saying that equal to 0. And if you look at this, everything has a 6, and okay, all right. Well, we'll come back to it. Let me not get ahead of myself. F sub y equals 0. So now take derivative with respect to y. Goes away, goes away. And this becomes minus 6y, and this becomes plus 6x equals 0. Now, let's think about what these equations are telling us. The second equation is a little bit easier to parse, so let's start with the one easier to parse. Everything has 6's in it, so the 6's cancel, and so this says minus y plus x equals 0, or really says, hey, y is the same as x. I think that'll be useful. Now, go into the first equation. This says, get rid of the 6's, x minus x squared plus y equals 0. But then we say, well, wait a second, y equals x. So we say, oh, okay, if y equals x, then I can replace y by x, and then we have x and x, so that becomes 2x minus x squared equals 0. And factoring x out, x times 2 minus x equals 0, which leads us to x equals 0, or x equals 2. And now remember, y equals x. So if x equals 0, y equals 0. And if x equals 2, y equals 2. So these are our points. Okay, so our critical points, we'll make a little list here. We have 2 of them. One of them is 0, 0, and the other one is 2, 2. All right, so here we have our box. And if you're wondering, why did you make your box so big? Because we'd have to talk about stage 2. We talked about stage 1, find. Now we're going into the next phase of our problem, which is to classify. Okay. So classify. Now, this goes into the second derivative test. Now, technically, it shouldn't be called the second derivative test. It should be called the second partials test because it's partials derivative. But we understand what we mean. We're among friends here. So we're not going to split hairs. So the second partials test, and what does that say? Well, it says, look at the second derivatives. So you have fxx, fyy, fxy, and that's telling you how the surface, in some senses, is bending from your critical point. Now, because we have our gradient is 0, our tangent plane is 0, so we want to know, are we sort of bending up, which means we're at a min, are we bending down, are we at a max, or maybe in one direction we bend up, and another direction we bend down, saddle. So all of that can, well, usually, unless things get messy, we determine by looking at this quantity, which is fxx, fyy minus fxy squared. And there's a few possibilities. All right, if this is negative, then what you have is a saddle. So in other words, you have it's going up in one direction, down in another, saddle. Neither min nor max. If it's positive, then you got to go into looking at a slice and channel your inner Calc 1. And you say, okay, well, let me look at, say, fxx. If that's negative, then we're a max. If xxx is positive, then you're at a min. So this is go all the way back. If you have positive second derivative, your slice looks like this. That's why you're min. If you have a negative second derivative, your slice looks like that. You have a max. Now, if you have equals to 0, you just say no conclusion, and you don't have to go any further because we won't ask you to go any further. So if it's 0, we don't know. You can keep probing, but don't worry about that case. Don't worry about that case. Okay, so we need to start gathering our derivatives. So let's do that next. We need all our second order derivatives. Okay, so here we go. fxx. All right, well, we have f sub x up here already, so we're taking the derivative with respect to x. And so that's going to be 6 and minus 12x, and derivative of 6y is 0 with respect to x. fxy. Okay, take the derivative of fx with respect to y. That's 0, 6. All right, 6. And fyy. All right, what is that? Well, come here, and we see the derivative with respect to y of 6x will be 0, and here is negative 6. Okay, so here we go. Our quantity that we're very interested in, sometimes called discriminant, is we take 6 minus 12x times negative 6 subtract 6 squared. All right. Whew. Okay. Now, what are we going to do? Well, we have to plug in. So at 0, 0, well, that says we're plugging in x equals 0. There's no y, so we don't need to worry about that. We get 6 times negative 6, subtract 6 squared. Well, that's minus 36 minus 36. And we could say it's negative 72, but we only care about the sign. We'll see the sign, and it'll open up our eyes when we see the sign. In this case, the sign tells us saddle. Okay, sign is negative. When D is negative, that tells us we are saddle. Okay, now, what happens at 2, 2? Well, again, plug in x equals 2, y equals 2. And what do we get? Well, we're going to get that we have 6 minus, to do math in my head. I'm getting old. I'm expected to do math in my head. Okay, 6 minus 24, right? Yeah, 6 minus 24, which is negative 18. And times that by negative 6. And then we're going to subtract 6 squared. Now, of course, negative 18 times negative 6 is, it's a number. And we could work it out. It's not actually super critical that you work it out. But if you wanted to, that's 108. And then you're subtracting 36. And, well, that's positive. Really, you just need to know the sign. And on a side note, you notice this is negative 72. This is positive 72. It happens a lot that way. Don't always count on it happening, but don't be surprised if it does. All right, now, what does that tell us? It tells us more work, right? Because when it's positive, it's a max or a min, but you have to know which one. And for that, you say, well, look at the signs. Now you can look at either fxx or fyy. So there's fxx, there's fyy. Here, we wrote down fxx. You can use either one, fxx or fyy. They're negative. Negative numbers. That means we're kind of frumpy, which means that we are what? We're at a max. So 2, 2 is a local max. Okay, and there we did, right? We found them, and we used the second partials test to classify. And saddle, I guess it said local max, local min. So max, max local. There we go. Ha ha ha. Local max. We should have specified it. Since it's specified local max, we should have added that. But there we go. There we go. And that brings us to our last problem. And don't worry, plenty of time. Plenty of time. We will finish. Use the method of Lagrange multipliers. All right. I bet you we're going to use the method of Lagrange multipliers. See? They kind of give it away. Sometimes the hints are subtle. Sometimes it's like, to find the maximum value for this function xy, given that 4x squared plus 2xy plus y squared equals 36. You do not need to prove that your answer is a maximum, which is good, because Lagrange multipliers really doesn't work that well for proving things are maximum. It tells you where to look, where you should say, well, if you think there's a maximum, here's where you should look for it. But it doesn't say, oh, and by the way, I promise you it is a maximum. It just says, hey, I only said this is where to look. You can't blame me if it's not the actual max. But okay, we don't need to prove it. So that's good news. So we're just going to run through the procedure. So what is the procedure? And what is Lagrange multipliers about? Well, Lagrange multipliers is constrained optimization. So in other words, we're trying to optimize. In this case, it's this function. And we know we're trying to optimize it because it says find the maximum for this expression. Okay, so maximize that expression. What's our constraint? Well, we're looking for something equals number. So that's our constraint. All right, so here we go. We're going to write it down again. So maximize, we have our f of xy equals xy given our 4x squared plus 2xy plus y squared equals 36. And we're going to think of this as our g of xy. Okay, so we have our f of xy, we have our g of xy, and we say, well, all right, how do we go about doing it? And here's the basic idea. The whole thing boils down to saying the following. You have one relationship already between x and y. We want to get a second relationship. And the way we're going to do it is saying, when you're at the maximum, compare the gradients. Gradient of f versus gradient of g. And how do they relate to one another? And so at the max min, we have that the gradient of f and the gradient of g are parallel. And so you have this factor, multiplicative factor, two things are parallel if they differ by a constant multiplier. That's where the multiplier comes from in Lagrange multipliers. And so we're like, nice. And so this is going to lead us to a system of equations, in this case just two equations, f sub x equals lambda g sub x, and f sub y equals lambda g sub y. So let's write down what our equations are in this case. So we have our function f. So f sub x would be y, and that's equal to lambda g sub x. Well, that's 8x plus 2y. Okay, then we have our f sub y, which is x. That should equal lambda times g sub y. Well, that goes away. That would be 2x plus 2y. All right, so here we have an equation. Now, we don't care about lambda. So here's the beautiful thing. When in doubt, solve for lambda. And so what does that mean? Well, we say, hey, look at this. Y divided by 8x plus 2y is lambda. But it's also x over 2x plus 2y. All right, I just solve for lambda. And you might say, don't worry about division by zeros, because what next step you're going to do says, haha, it doesn't really matter. Which is, say, look, ignore the lambda and cross multiply. So here's a new relationship for x and y. We get that y times 2x plus 2y is equal to x times 8x plus 2y. And, well, okay, let's clean that up. We get 2xy plus 2y squared equals 8x squared plus 2xy. The 2xy's cancel, almost like we want you to have a chance. Well, we do. We want you to have a chance. And we can even divide by 2, and so we get that y squared equals 4x squared. Okay, so our new relationship is y squared equals 4x squared, which notice that splits into two possibilities. Y equals 2x, y equals negative 2x. So imagine you take the square root of both sides, but when you do square roots, you always have that plus or minus coming into play. Okay, cool. All right, now, this we're going to mix in with our original constraint. So let's go ahead. Everywhere we see a y, we're now going to put 2x. So for y equals 2x, we have 4x squared plus 2x times 2x plus 2x squared equals 36. And let's see, that's 4x squared plus 4x squared plus 4x squared. Oh, there's a lot of x squareds going on here. But okay, 4 plus 4 plus 4. That's 12x squared equals 36, or x squared equals 3. So x equals plus or minus square root of 3. All right. And so what does that give us? Well, that gives us the following points. Square root of 3, comma, 2 square root of 3, and minus square root of 3, comma, minus 2 square root of 3, because y is twice x. Now, same procedure, but we do it for y equals minus 2x. Okay, we use our constraint. 4x squared plus 2x times minus 2x plus 2x squared, minus 2x squared, excuse me, y equals minus 2x, equals 36. Now, something a little different happens here. Here, 4x squared minus 4x squared goes away. So this becomes 4x squared equals 36, or x squared is equal to 9, which says x equals 3. All right, so where are these points? Well, they're at 3, well, plus or minus, I forgot to say that. So x equals 3, y is minus 2 times 3, so that makes minus 6. Or negative 3, and then minus 2 times minus 3, positive 6. All right, so what's the punchline? We're almost there. The end is near. The end is near. What we've done is we had what we're trying to maximize given our constraint. Constraint looks like function equals number. We said, well, that's just one equation. We really need a second equation, and that's where saying the gradient equals lambda the gradient gives us a new relationship. And now, with two relationships, we solve for our points, and we have 4 points. Our max and our min will occur somewhere on one of these 4 points. Now, we don't need the min, we just need the max. So what's our last thing to do? We need to plug each one of these points in. So let's do that. Where do we plug them in? To our original function, x times y. And so we say, okay, so if we plug in root 3 times 2 root 3, just multiply these together. Well, root 3 times root 3 is 3, so it really becomes 2 times 3, which is 6. And, all right, f of minus root 3 minus 2 root 3. All right, the minuses cancel. It still gives you 6. F of 3 comma negative 6, multiply those together, you get negative 18. F of negative 3 positive 6, multiply those together, gives you negative 18. And now we say, okay, these were where max or mins could occur. These are the corresponding values. Which is the largest number on the list? And the answer is 6. So this must be the max. It's the biggest number. All right, so max equals 6. And on a side note, it occurs at square root of 3, 2 square root of 3, and minus square root of 3, comma minus 2 square root of 3. We don't technically need that. In fact, we definitely don't need it. But just be ready. Sometimes they may ask you for that. And this gives them confidence, like, yes, this person definitely knows what they're doing. All right, what a good way to finish our problems. Cooling down. We did it. We did it. All right, well, an interesting test, some interesting problems. I'll tell you, that multiple choice, whoo, what a ride. What a ride. And but don't worry, you can do these problems. These are problems that you are capable of. Make sure you're doing the work. That's why you're here, and I'm glad that you are. Thank you for working so hard. Keep it up. I believe in you. Good luck, and I hope you do well. And then let's see each other one more time. Okay. Bye.